One of the types of reactions that we talked about before can actually be used to determine the empirical formula and then by extension the molecular formula for different compounds. And specifically what we're talking about here is using the combustion reaction in a technique known as combustion analysis. So the idea behind it is actually very simple. We can take a substance uh, or a sample, whatever that sample happens to be, and we can subject it to combustion. That means reaction with oxygen. If we do that in a furnace, and then what we can do is once the gases are produced, we can funnel those gases through different regions where the different products are trapped at each station. So for example, when this, whatever this sample is, let's say it's a carbon containing compound, we burn it in some oxygen, we get CO2 and we get H2O, and then along the way, where those gases are exiting our reaction chamber or our furnace, along the way, we can actually now trap those products. So for example, there's a H2O absorber over here. If we know what the mass of that absorber is before the reaction, and then we can measure the mass of that absorber after the reaction, we can determine the amount of H2O that was produced. And then similarly, if we have another absorber down the road, like a carbon dioxide absorber, when the gases are produced over here due to combustion, right, the CO2 gets trapped over here. We can measure the difference in mass from the beginning to the end of the reaction. We can calculate the amount in mass of CO2 that was produced in that reaction. So the idea here is that the amount and specifically the mass of each of these products, H2O and CO2, can be determined experimentally. And based on those numbers, we can then work backwards and we can figure out the original amount of the reactant, and then we can do some calculations, stuff that we used before to determine the moles of each of the components of that reactant. So let's take a look at an example of how we could do this. So let's say that we have, in the combustion of 18.8 grams of glucose. Okay, so we know that we are starting here with a certain amount. So this is our sample that we're putting in the combustion chamber. We know how much of that we're putting in and we know what that is. So it's 18.8 grams of glucose. And we know we have to have some basic information. We know the glucose is made up of carbon, hydrogen, and oxygen, right? And then we've subjected to the process we described before. And then based on that and the absorbers that we have at the end, we found that we were able to produce 11.3 grams of H2O. And then we're able to produce, what do we have here? It's purple. We're able to produce 27.6 grams of CO2. Okay, so we can actually use both of these values and we can work backwards and we can figure out how much of the carbon and hydrogen we actually had in the original sample, which was our 18.0 grams of glucose. And we can do some very simple calculations to do that. So for instance, if we know that we have 27.6 grams of CO2, right, we know the relationship between grams and moles. We can convert that to the moles of CO2. We're going to use the molar mass. Of CO2. And then just based now on the formula of CO2, I can calculate the moles of carbon. Because according to my chemical formula, every mole, okay, 1 mole of CO2 has 1 mole of carbon. Because I just look at the subscripts in my formula, because the subscripts do give me a mole-to-mole ratio. All right. And if I know how many moles of carbon, well, then I can convert that to grams of carbon. And I use the molar mass of carbon. And where would that carbon come from? Well, the carbon has no place to come from other than that sample that I used, which was the sample of glucose, right? So I can determine how much carbon was in that glucose to begin with. And I can do the same thing for the hydrogen, right? So if hydrogen is in this glucose and I subject it to combustion, the only product that I'm going to get that has hydrogen in it is the water. So I can do the same thing with the water, take the mass of the water, so the mass of the H2O, I can convert this to moles of H2O, which is by use the molar mass, and then I can convert that to the moles of hydrogen, and I use the mole to mole ratio that I have in the formula for H2O. So 1 mole of H2O, okay, actually has 2 moles of H, right? That's from the formula, and that's my ratio here. And once I get to moles of H, I can then convert it to grams of H by using the molar mass of hydrogen. So I can now determine how much grams of hydrogen was in my original glucose. So I know in my glucose I have whatever grams of carbon, depending on my calculation that we just outlined. I know how much hydrogen was in that original sample. Well, the only other thing present in my glucose is oxygen, right? So if I know the total mass of the glucose, which was 18.8, I can just subtract the mass of the carbon and the hydrogen, and then I get the remaining mass, which is going to be my O. So I know then that I would have 10 grams of oxygen. So I can determine it by going through these calculations, I can determine the masses of C, H, and O in my original sample. That is not a formula, that is just a ratio of masses. What we need is we need to convert these masses into moles. So we're going to convert them to moles of each of those. All right, so in order to convert to moles, we're going to use the molar mass for each of those things. So I have the grams of carbon that I calculated, molar mass of carbon, 12 grams per mole. I set it up so that the grams of C goes away, and I get 0.627 moles of C. So now what I can do is I can start writing my chemical formula now. Remember, your subscripts in a chemical formula gives you a mole ratio or moles that you have in each. So I have 6.627. And then I have H. Well, I know how much grams of H was in there. I divide by the molar mass of H, so the grams of H go away. I get H now 1.25. And then the O, which we determined was 10 grams, divided by the molar mass of oxygen, which is 16. That gives me 0.626. Okay, so I have my rudimentary um, chemical formula. So let's rewrite that. So I have C 0.627, H 1.25, and then O 0.626. Okay, I'm going to divide all of these by the smaller of the numbers, which is the 0.626. Divide all of them by 0.626. And obviously this cancels, that gives me 1. This is going to give me 1 as well. This one here is going to give me 2, so I end up with C1H2O1, which is the same as CH2O, as the simplest whole number ratio, which is your empirical formula. All right, so that would be the empirical formula for glucose. If I wanted to determine the molecular formula, then I have to know uh, the the molecular mass, right? So this here, I'm sorry, this is the empirical formula, the simplest whole number ratio. to determine the molecular formula, we would need the molecular mass. And what we can do then is we can divide the molecular mass by the empirical mass, and that is going to give us a small whole number, which is going to be a multiplier. And what we do is we multiply the subscript, multiplied by the subscripts of the empirical formula. Okay, so in the case of the one that we just did, the molecular mass, approximate molecular mass is 180 grams per mole, the molar mass. The empirical mass, based on the empirical formula, I have 1 carbon, 2 H's, and then 1 O. That gives me about 30. So I take my molecular mass, 180, divide it by 30. So 180 divided by 30 is 6. So I take my C1H2O1, and I multiply each of these subscripts now by 6. So that's going to give me C6H12O6 as my molecular formula for glucose, based on that combustion analysis, right? So the idea behind the combustion analysis, we can use the amounts of carbon dioxide that is produced. We can convert that to moles of CO2, then moles of carbon, then grams of carbon. We can use the mass of the water that's produced to convert that to moles of water, then moles of hydrogen, then grams of hydrogen. We subtract the sum of those two from the total mass of the sample. We get the mass of the oxygen in there. We're just converting to moles from that point onwards to get the mole-to-mole ratio of each of the C's, the H's, and O's that we have in that compound to get the empirical formula.